let's discuss actually example one from the book. And again, there's something which I completely disagree with the strategy of the book, as they introduce a change of coordinate given like this by those expressions, and the book does not verify that the change of variable is indeed one-to-one, that we really do have a change of variable. If it is not one-to-one, this is not a change of variable. This is something that we must check. And it's not necessarily very easy, and you will see here, to prove that to prove that this change of variable is really one-to-one is not easy. There is, I must say, a fast way to verify that it is indeed a change of coordinate, which a nice change of coordinate, by using complex variable. But I'm not necessarily assuming that everybody knows complex numbers, so we will do it without it. And we will revisit example one together. All right, so this is the transformation. Phi of uv equal u squared minus v squared. This is going to be take place of x, and y is going to be 2 times uv. And the domain on which I'm applying this transformation is simply the unit square 0, 1 cross 0, 1. All right, so x equals u squared minus v squared, y equals 2 uv. So what I want to know is that is it really one-to-one? So what I want to make sure is that if I take 2 points here, can they have the same image? Is it possible? And I want to show that no, it's not possible. If 2 points on the square are distinct, their image should be different. Or assume that we have 2 points of coordinate u1, v1, u2, v2, mapping to the same thing. So what does it mean? It means that u1, v1, 2 u1, v1 equal to 2 u2, v2 through by saying that the second coordinate is the same. So in other words, well, okay, this means what? This means that those points sit on an equation u1, v1 equal u2, v2 equal k. So that means that this is on a hyperbola y equal, let's say, I should say u equal k divided by v. That's what it says. So that's why I say that we always have a relationship between u1 v1 and u2 v2. It says that the product of the first component and the second component is constant, is k. Or in other words, we sit on this hyperbola. All right. Now, what does it take? When you look at the second coordinate, we still need to have u1 squared minus v2 squared minus v1 squared should be equal to the image of the first component of the image of the second point, u2 squared minus v2 squared. Now, we replace u1 by k divided by v1, u2 divided by k v2, and we have, therefore, this equation, k squared divided by v1 squared minus v1 squared should be equal to this. All right, so this is the equation that needs to be satisfied by means of v1 and v2. Alright, so v1, v2 belongs, you see, to this interval 0, 1. Now let's introduce this function. I call it depending upon x. X has nothing to do with that. This is so I probably should not call f of x, but f of t. Well, look at this function. This function, which is a function depending upon one variable that you can probably understand by means of classical calculus 1 theory. And we have to look at the value of x between 0 and 1, because this is precisely where v1 and v2 sit. They cannot be bigger than 1, and they can't be negative. It says what? Well, we have two values, v1 and v2, such that the value of the graph is the same. I claim this is impossible. Sorry, it should be like this. I claim this is impossible. Why is it impossible? Because if you differentiate this function, you have something which is always negative. Remember, x is positive. Look at that. It's always negative. Actually, it tends to infinity when x tends to 0, and it's equal to k minus 1 when x is equal to 1. But it's always negative. So the function being always decreasing, this thing cannot happen. And this means that for this to be true, it means that v1 and v2 must be the same. Alright, so v1 and v2 are the same. Well, that means precisely that thanks to this equation that u1 and v2, u1 and u2 are also the same. And therefore the map is really 1 to 1. Alright, so that's one thing. And you see that it's quite time consuming, and it was not easy to it's not easy to verify that a map is always one-to-one. That's also a disadvantage of this method. Now let's look at the image. So let's merge what was done in the book by looking at the image of this domain. So I'm going to erase everything which is not relevant from what we are going to talk about, and I'm going to use exactly the same principle. This transformation now is not linear anymore, but still maps boundaries to boundaries. It's clear that the origin will be mapped to the origin. When u equals 0, v equals 0, we have the same thing. So now let's look, for example, at the image of the line phi. So I like to have v equals 0, but u varies between 1 and 0. I will get a curve parameterized by u and see what this curve will be. Alright, so what is it? So you just replace v by 0 and you got x equal u squared and y equal 0. Right. Oh, that's interesting. So it's a curve which is like this, which is simply sitting on the set y equals 0. So it's on the x-axis. But you see that x varies between what? Since u varies between 0 and 1, x vary also between 0 and 1. So we have something like this. Let me draw it like this. So this is the origin. And this guy here maps this segment, which is mapped onto this segment, 0, 1, precisely. Right, so that's one thing. What are we going to do next? We want to look at the image when not v equals 0, so not this one, but when v equals 1. Alright, so this time you're going to get u squared minus 1, but now we're not going to get 0 because u is different from 0. V is different from 0, sorry. You're going to get, what is it? V equal 1, so 2u, simply. Okay. So this is nothing else than a curve. A curve that, I mean, I can get rid of u here, and I say that x is equal to, so what is it? U divided by 2 to the square, so u squared divided by 4 minus 1. Alright? Which means what? Which means that it's a parabola. So we have what? What are we going to? How are we going to set the things up here? When so u varies between 0 and 1. So let's look at first of all what is the value when u equals 0. Well, u equals 0. We have x equal minus 1. And y equals 0. So that point is, let's say, it's nothing else than the image of this point. And then we have to look at the image. Let's say we have to pretty much figure out what is this this guy. So x between being so u between 0 and minus 1. That means that x is negative. So x will vary between this interval, and y will vary accordingly. So how to draw a graph like this? So how does it look like? So it will suddenly hit this axis here. So when does it hit this axis? When is x equals 0? When u is equal to 1 here. And when u is equal to 1, we have y equal to. So this is a curve, let's say like this. So this is the image of the boundary. So maybe I should put red lines. So 1 is mapped here. This side here, let's call it 3, is mapped here. Right? Now, is it enough? I like to look at the image when now I fix u equals 0 and v varies between 0 and 1. So raising everything here. So what is the image of this side? I'm going to call this side number 4 as being this one number 2, if you don't mind. So what is the image of v of v equal, no, it's u equals 0, sorry. This time is u equals 0, but v varies between 0 and 1. Alright, so now you got x is equal to minus v squared, and y is going to be equal to, well, 0. Alright, so this time we again have a segment, but this time it's located not in the positive, on the positive value of x, but negative values of x varies between 0 and 1. So this is the image of 4. So that guy is mapped to this guy mapped to this, and that guy is mapped to that. Now we'll like to look at this, the image of number 2. So I need to put u equal 1 this time. And what I'm going to get, not this expression, but 1 minus v squared, and what do I get here? 2v. Well, pretty much I'm going to get a similar expression. X is going to be equal, this time, 1 minus y squared divided by 4. So it's an equation again of a parabola. Let's look at the extreme point when u equal 1 and v equal 1. So that is, I'm looking at the image of this point. I get x equals 0, but y equal to 0. That's exactly the same point here, which is not so surprising. We already computed. And now finally, when v equals 0 and u equal 1, what do you got? So v equals 0 give me x equal 1 and y equals 0. So this is this point. Actually, this equation was exactly the same equation as we get before with the minus sign. So they get exactly this shape. And now it tells me that a point here is mapped to a point here in this domain. I have to observe that this is not a super easy thing to see in the first place. Finally, this is something that we need to compute also, is the Jacobian. The Jacobian of the transformation when we're going to consider a change of variable. So actually this is one of the further example where they ask you to integrate a function on this domain. So you don't do that, don't do that directly using iterated integral, but by using this change of variable, and it making your life in general much easier. So how do we compute the Jacobian? Well, exactly the same way, and that's not the hard part to do. So dx over dy, dx over du is 2u, dx over dv is minus 2v. What is dy over what is dy over dvu? You got dv, 2v, and then 2u here. So what is the determinant of this matrix? It's equal to 2u squared, 2u to the square makes 4u squared, plus 4v squared. Observe that this is something which is never vanishing. Actually, we are always tempted to say, if the determinant is not vanishing, then the map is 1-to-1. Is it true? Well, yes, it's true, but it's only true locally. Means near a point, if the determinant is not vanishing near this point, then the map itself near this point is going to be 1-to-1. But it doesn't mean that it's going to be globally 1-to-1. We need to work a little bit more. If you look, for example, at the case of the polar coordinate, r cosine theta, r sine theta, and you allow theta to vary between 0 and 4 pi, say, well, we know that every 2 pi we have the same value because of the periodicity of the trigonometric function. So this map is definitively not injective or not 1-to-1. So we won't get this. That's the problem. So the map is not 1-to-1, but if we restrict, of course, the map onto the interval 0 to pi, the set of points on the r theta space for which the map is not invertible, is of no area, in other words. So we still can use the theorem, of course, for the polar coordinate, but we cannot definitely cannot say that if a point, if the determinant is vanishing anywhere, then the transformation has to be one-to-one everywhere. That's unfortunately not true. We have to check it point by point, this in the same way as we did before. All right, so in the next video we'll go more toward the aspect of how to integrate and also taking into account how does my transformation look like, and what does it do? What does the transformation do? From which space to which space are we operating? Okay.